Okay, here we go. It's going to be a knowledge dump. I'm going to show you how to build a device just like this, but that performs better, costs less. This is an $89-ish product from Rigid, sold at Home Depot. It's pretty much a class-leading offering for getting PD, USB-C, PD, power delivery output from a power tool battery. And Rigid also has, I think, the best power tool batteries. You can pretty well abuse these things because they have thermal control. If you bring it outside in the hot or the cold, then it shuts off if it's out of spec for temperature. It has a power indicator built in. They have lifetime warranty with free replacement. And I'm not even worried about whether we're preferring the Rigid cells. I'm indicating that when you have something that is this competitive, there's millions of engineering hours behind it. They have a nice big market share, so whatever we design that goes along with a cell like this, a battery pack like this, becomes incredibly useful immediately because other people have the ingredients, the components to work to produce the same outcome or similar because we've already got a standard. Okay, why is it important? Why is this the most important thing for the device? It's because getting 45 watts out from the USB-C is like a high power delivery for new appliances. And in the past, we were looking at something like 10 watts for a USB port, 2 amps, 5 volts, and now we can get up to 20 volts or maybe even more. New appliances are coming out continually that can take advantage of that high wattage. And I want to reuse all these wonderful batteries to do things like soldering. So when you grab one of these modern soldering irons, we can go up to 80. Wow, that's so flexible for the input, but 24 volts, we're going to get around 21 volts out of this and crank it up fast. Now, Rigid thought the most important thing here was the inverter, right? So you can get AC output from here. But with all the new things coming onto the market, we're going to use DC directly for most appliances when possible, because the inverter is just a good way to lose 20% of your energy all the time, no matter what. All right, so another constraint is we got 2 watts of constant draw when this is powered on. You use the machine, you press this button to access the power, and then if you forget to press that again, then you're gonna lose the next morning, the whole battery will be drained, even if you only used 10% of it for your work. So we have a very big shortcoming in my opinion. There's a reason they designed it that way. It's because it's probably worse if you were expecting the machine to work and it just timed out while you were pulling power from it. But that's not my problem. My problem is this thing quietly draining the energy away. So now you're looking at something called Terminal V2. This is a new build for the terminal component that I've posted on GrabCAD. The first version was it was one piece. It was similar to this product that some gentleman designed, built, and sold on eBay and Amazon in the past, a few years back. So I purchased this without the region in my left hand. This is a scuttle apparatus to give me some ports and a switch, but so it's a popular device already. People are accessing the power from their batteries. And you have 2 off-the-shelf. These are from something like Mauser. You'll find connectors. Those are a little bit challenging to find, but I found at least a good selection, and I've open sourced it. So we're looking at Molex 44262 series of connectors, and then a geometry here in this 3D printed device that lets you slide them in. And then I've done when you cover it up, it's going to cover them, prevent them from falling out. The base of these connectors is seated into the 3D plastic. So this is printable with no supports, as always, per my 3D printing design rules. And it'll operate just by itself, so you can hook this up. It's going to slide in here, and those terminals will go. If you download this model, then there's part A and B. Essentially, A is here. You can print this out, and now you can get access. You can crimp your own terminals to your own wires. These are, I think, common for all my projects is 18 gauge, and this is a little bit larger, so call it 14 gauge. That's enough to carry at least 20 amps. And our Anderson connector. This is just one way to connect. In any case, once you have this module, this is the simplest possible geometry to both connect into your battery, the minimal amount of material and complexity to access those terminals, get power. And then you have something, when you combine them, you have something that's a little bit closer to, so these go together like that. It is one CAD model to have both of these with two bodies, two solid bodies, as in SolidWorks. So these go together, and then a screw, if you want them permanent, then you can fasten the screw in the left hand and the right hand. That's M2.5, and it'll go in here. Okay, so we can work with these separately, which gives us a lot of freedom for new designs, more flexible assembly, but also grab this open model and adapt it to make the thing that you want with the type of terminals you want, or grab this one and attach whatever you want. Here's a quick demonstration. We choose vehicle lamps. Nice, beautiful, rigid lamp with a good brightness and aluminum housing. This is going to be a lifetime device, and it'll work just like the ones they sell for power tools, but now it's flexible. You could do two of these in parallel, and this is easily going to provide the power that you need. Now, where do we want to attach this? Somebody might want it on a big lever. Somebody might want it mounted very closely to the battery so that the mass of the battery can be the stabilizing thing. All right. So the next step will be to take these, combine them, and that will get you this. So we've connected the terminals. We've passed them through the two holes in body B, version 3.3. And then we're going to have the wires routed wherever we want. And we're going to get these two holes on our handy box. This is an off-the-shelf $2.50 device, electrical outlet box. It's very, very standard, very available. Sorry, it's more oriented towards North America. Canada has another slight variation, and I don't know what all is going on in Europe, but we're trying to help you guys too. Europeans, I'm sure there's an engineer that can come up with something along these lines. And again, open source geometry means maybe you can just adjust one little feature like these and the holes to get compatibility. All right, so now you've got wires in a box and probably 500 watts you could pass through here. So what happens next? Well, I just got done painting this. So we're going to reintroduce those Anderson ports. Okay, so now we can just plug in like we wanted to before. And then we have this device. It may be called a cigarette lighter or a car power outlet, something along those lines. But this will be added into that hole, fastened down, but still removable mechanically and electrically. And then we are going to add our USBC power delivery adapter that gives 65 watts. So our device will have higher performance than the market leading off-the-shelf device, costs less, and is updatable because you can change this next year when a new gadget comes out. So let's build. This little piece of PVC is just helping to adjust. We want our fastener to not tighten down all the way to this radius where it kind of bumps up against the corners interiorly, in the interior corners. So this is just a spacer. You can craft that out of anything that you want. And then we're going to get our big round nut thing. You can tighten that by hand and it'll probably be sufficient. Definitely going to be sufficient for today so I can get through this tutorial. All right, So now we have Anderson on one side, and we have leads because we have made a Y junction. Your wires, use basic soldering skills, heat shrink that carefully, and then you'll have red for 20 volts, black for 0. All right, so I'm gonna stick that down. We're gonna get that connected, and then it'll be a matter of just coiling these wires neatly enough. And you wanna do this while the battery is not connected. Coiling these, pack these wires into the apparatus, which is also why, you know, the handy box is larger than it must be to work for this design, but it sure is nice to have plenty of extra space to pack wires instead of making it too tight, basically. All right, so I'm just looking for my holes. There we are, we're lined up. And okay, so the screws, we're using M4 metric screws, which are just slightly larger than the size that comes with, I think this is 832, 8-32, number 8 screw. That's an imperial thread, thanks Britain. And I've boarded out, or I've re-tapped it so that it's now metric 4 millimeters. And that gives us a little bit better clamping force between the screw and the electric gizmo. You can maybe see the screw reaching in there thanks to that small gap there. And then we're going to put another one over here. And I used, this one's countersunk, but it's intended for a flat-headed screw. Okay, so now we're fastened. We have one unit. And these screws are M2.5. They've already been threaded in. They don't even, we just have a slightly undersized hole, and because we're not going to encounter pull-out forces, we just need those really to act like a pin. So there's just little interference between the plastic in this hole and that screw, and that's sufficient for this design. We don't need to have carefully thought out threads or a heat set insert, etc. All right, so now we should be looking for the light to light up when I slide this on. We have this little pocket here, just carefully placed not to interfere with the screw, but also still to match up to these springy things. Now we're lit up. Okay, we have Anderson, and then we should get the green light plus our, I think, blue light on this one. Boom! Okay, so the beauty of this is I've already tested the power. By separating the device from the battery, we're pulling less than 1 watt. And I've already tested that. So we'll have twice as much life leaving this on. And you can also make a variation on this. If you want to switch off the power entirely, I've built this also one with a switch. So this will isolate completely the battery from anything on the outputs. This one doesn't have the cigarette lighter. It just has Anderson and does the same thing. Then this metal shell, which I've painted gloss black, matte black, that becomes a mounting feature where you can go and build your next design feature. So if I want to mount this on, I could bore out one of those holes just slightly and thread this in. Then I can still change my mind if I want to. And just having that rigid wall is fantastic for adding new things. It's much, much nicer than having just a plastic 3D printed housing. So HandyBox helps us out again. Now, let's just quickly demonstrate with the USB device. This lovely cord here has just been way more valuable than I expected when I bought it, so I bought another one. It's going to, when we power something on, it'll tell us the power level within something like 0.1 watts. So, and it'll indicate PD if we're doing the power delivery communication that asks for a voltage besides 5 volts. That's how PD works. Okay, so if I press right here, I think it's going to go for 350 degrees, 12 watts, 52 watts. Attaboy. Okay, so we have exceeded the rated power of the rigid device. We're getting really the most we could get. Look, we're already at 370 degrees on this iron, and that's not even a real small iron. When you have this amount of power on your, and it's an efficient soldering iron, you can do a lot more. And so this is, I think, for all the range of soldering to be done, this will accommodate twice as many things as one of our low-cost Weller devices. All right, so this is 42 watts, but that's the power draw. That doesn't talk about how much heat reaches the tip, and so that's a specialized tip. But anyway, we have on a device like this, it is less efficient in that more heat is exiting along this steel zone, and we get less heat at the tip right where we need it. And this one, it's just wonderful. So the prices of these are going down. There are similar brands besides this one. This is Pine Sill. So I'm happy with this one. I was happy with the other. All right, and now it's only taking 11 watts to maintain the temperature. Let's go on to the next feature. So while we're still heating up the iron, we better make sure this is turned off. Yeah, that's off. We have an adapter that's going to pretend this is called dummy. It's a dummy for a battery, so it'll still send the power, but there's obviously no battery there. We're going to get our power from somewhere else. And then we're going to power that on. Oh, yeah. No problem, boys and girls. And so there you have it. You do not have a DC power out feature on this. And it's, to me, the DC out is more valuable. We've beat the market leader for less cost, and it's open source. In the coming years, I think you will find more and more gadgets just wanting the direct power in the range of 18 to, it's rated at 18 volts. It goes up to 21. This one, while I'm running it, well, I can demonstrate. I'm going to hook up this meter. Okay. And then we're going to look at how much power gets pulled, how many amps. We're starting at 20.5 volts. So when we draw 150 watts, this comes down by half a volt. This is a healthy battery, though. This one, yeah, a more aged battery or a more used up one would probably drop more than that. In any case, now we have sufficient power and sharper new tools on our jigsaws and routers and many things. We can cut metal with these types of things. There's so much, so far that we can go working with some of the traditional tools in brand new ways. And so this is why in this lab overall, I want to get new modular jigs to hold this and make this into a benchtop tool. I've spoken about that a little bit in short videos, but imagine now we have some sort of tabletop. Can we bracket this onto a flat steel rigid surface? Can we do the same with the jigsaw? Can we roll these out to areas where we have to do the work? The initial purpose of this was, well, the most recent need I had was to do some soldering in my car, in the vehicle. I've got to disconnect the battery and solder on a wire. Then where am I going to get that power? I don't want to run extension cords like I would need to back in the old days with something like this. So we don't have to use Anderson if that's not your favorite connector, but that's just what I'm going to commonize across the Scuttle robotics equipment, the lab equipment, and instrumentation. So let's say you don't have this socket on this end. Ooh, by the way, I'll show you about. I'm really pleased with this adapter. That's only $10, and it's made by a little knockoff brand that seems to do really high quality work. I haven't heard of them until this week. This one's called Akizer. So there's gallium nitride involved, and I just know that because they're so it's so compact, and it is ever more efficient every year. I'm finding these at something like 95% efficiency, the power in versus power going out. And when you take 18 volts and drop it down to 12 volts, if I want 12 or 5 volts coming out of here, dropping down is much more efficient than going up. And so for years of projects where I needed just to say a metered power source, this is not just, a solution for when I need portability. This one is better overall solution for me to do some high-powered device prototyping and testing, even compared with these benchtop power supplies. So if I could only have one between this elegant little benchtop power supply, this one still maxes out at 300 watts. And if you're only at 10 volts, then you've only got 100 watts to work with. 10 amps is the limiting factor, and we can do more with that one. So yes, the suggestion is, even in engineering labs, we're doing learning and measuring. This is good for a certain range of accuracy that you may need, a certain duration. If you got to have something plugged in for a whole week and a steady output, all right. But if we're testing something that's going to be portable, it's just going to draw a lot of power to simulate a real work scenario, there we go. Oh, right, I was going to mention your favorite connector. If you don't want to use Anderson and you want to use another type, that whole feature is dictated just by this parametric sleeve. And so I published this maybe a year ago, which will fit into the socket, the cutouts, knockouts on the box, and then adapts it for the shape that you want. There is one extrude cut in a rectangle shape that determines this function. And so the way this one works is you set the Anderson terminal in there, and then you'll notice where we have this spring pin, that'll be instead M2.5 screw. So it'll line up to the right location, and we'll drop that screw in there, and then it's just locking it in place. It doesn't need to thread into these. It is simply acting as a pin. And when we if this had to be compressed just a little bit to go into the wall of that box, then when you insert these, it stretches it back out and helps retain it in its position. If there's trouble with retention, then you might add a little adhesive. And so I think this one is, I've added some glue there. Hot glue will do, or what do you call that? Yes, contact adhesive. So E6000, even without the premium, works fine. Now, the reason I mentioned hot glue and contact adhesive is because it is still somewhat removable. Unlike the PVC glue will melt and form into the plastic of this device, and probably it would take a destructive removal to take it out, versus contact adhesive or hot glue. It's going to give you the security that you want, but still mind changeability that you might want until you get everything configured. So that is the value of the open source, and its intention is that people can still pivot the designs to suit their needs. Improvements, a huge amount of effort goes into making this very, very nice so that it is something that is worth improving on. Sharing the STL file gives you, okay, 1,000 people can download and print this out, but then you're going to have a couple of designers who are really talented. We want to give them a head start and say, start here, because we have a well-made model with all of the titles added to the features in the feature tree, and it's easy to read, easy to recognize, and it comes with the package of data, a PDF that includes the information and research gathered for this, because this they may want to change this as well. So we're really trying to put the engineering out into the open source, not just a copy of the result. Okay, now think about this. I never dreamed this would happen, but Rigid is owned by Emerson Electric. They've got loads of engineers. Their market capital value of this business is $75 billion. And they work for me now, because this is my creation. And when they improve this battery, makes the next generation of this, then they will be enhancing my design. This is what happens when we can take the time to appreciate what did the engineers do to create value in these creations, and then capture that value and respect what is on the regular market that is doing amazing jobs, and anticipate how is this unfolding, because we've seen these continue to sell for 10 years. And Rayco, they manufacture this box. Those engineers are working for me because I have studied their design enough to say this is worth taking into our design. It's mass produced. The logistics are performed by Rayco. The advertising, the updating of all the drawings performed by Rayco. And then we have something here that outperforms this with, I mean, basically 45 watts versus 60. Idle power 2.2 versus 1. DC output, no versus yes. It's probably more than 200 watts. And we have the total cost, 85 versus 20. So, wow. We can really do this, guys. You don't have to be a huge company. You can leverage the huge companies. And then this is my message to Elon Musk. We imagined that technology, the purpose of technology is to design things and release products with higher performance, with lower cost and longer lifespan from the very first thing we release, okay? And that is compared with the market leader through technology. Elon, do you remember this car back in 2012? We brought your cars over to Toyota. This is the Toyota Design Center in Saline, Michigan, okay? And all of us engineers, Americans from all around the US, we were working here. We checked out your cars. Of course, naturally, we were doing benchmarking, okay? And I took this for a weekend. I stuck my girlfriend in it and evaluated what are you designing and what are you releasing. And Elon, we were listening. We heard the messages coming out of your company at Tesla. We thought you were going to give us higher performance and lower cost and longer lifespan. We thought that you were going to outperform the state-of-the-art technology with all the resources that you had access to. And if that were true, if this thing had the mileage and the cost, and it had the performance that was going to last longer than a Toyota, then I would be working for you today. So I don't know what to tell you, but it can be done. It can be done from the very first product, and you don't have to do this. You don't have to do this. Oh, we're going to make it first cost twice as much, and then later think about how to reduce the cost. No. That was Michigan. Now I'm in Texas. And I have several friends that are now working for you. You came over to Texas after me, an hour and a half away from here in Austin. You're setting up your plants. You're still building. It's more than 10 years later, and you still haven't made cars cost less. We're disappointed. We're disappointed. And my pals that work for Tesla are not, they're there for their paycheck. And I watch them go home and do their very best, most passionate work in their backyard, in their garage, in their living room, on projects where they can finally put their creativity and do something that really comes from their inspiration. So you're missing out on the inspiration of a lot of engineers, and you already know why. So hope you guys enjoyed this video. I hope this is something helpful to you. Your feedback and your inputs are always welcome. And if they're technical inputs, put them there on, so we have qr.net/openlab project. And we have OpenBox, which is an array of the designs that relate to this handy box and some of the great things you can do with these handy boxes. So if they're technical inputs, drop them there in the GitHub repository where we've got the discussions about this stuff, or on the GrabCAD where we've posted the, I posted my models. And any other questions that if I need to add the vectors for the content, then just let me know in the comments of this YouTube video, and then I'll keep posting. Thanks everyone. Hope to find more collaborators. I hope I find one solid collaborator who's interested in these battery and power related projects from this video. Have a good weekend, guys.